Hello everyone. If I show you these scalar fields and ask you what is the gradient, let us say at this point or at this particular point or at this point or this point, if you are unable to answer it, this video is perfectly for you. At the end of the video, you can tell the gradients of these figures and even much more complex scalar fields as well. Before going into 3D, let us see how the gradient works in 2D. So here I have the function f of x equal to x square, a parabola. Suppose you are at x equal to -1. And if I ask you in which direction the y is changing more, and intuitively you will tell that direction is in the negative x. The computer doesn't know intuition. It follows a systematic procedure. Let us say you are at x equal to -1. Now you take a step from x equal to -1 to x equal to 0 and you will tell that y value is getting decreased, so the gradient should be in the negative x direction in order to make it increase. But some other person may say my step is larger than yours. If the person moves from -1 to directly to 2, then he may say that this positive x direction I'm having the largest increase in the y, so the gradient should point in this direction. Now which is correct? So in order to estimate the change in the y, we need to consider the step size as well. By using only the change in y with respect to 2 points, we cannot tell because the step size even matters. So when we consider the step size, so it becomes del y by del x. Now we will get the change in the y per unit x. Now when we try to decrease the x less than that unit, when we turn the x to 0, that's when we will get at that particular point in which direction if you move, you will get the maximum y value change. When we turn the delta x to 0, we'll get the slope or gradient at that point. Computer doesn't know the limits. How does it compute it? Computer takes h to be very less value, like in the order of 10 power minus 6 or 10 power 8, and then mathematically substitutes the value in the function, and then it does subtraction and then division by h. So that's how the computer computes the gradient. And if you look back at the figure, if you calculate the gradient at x equal to 1, you will get 2. So when you are at x equal to 1, if you move in this positive x direction, it means the y value is changing. And similarly, when x equal to -1, the gradient is -2. Here, because it's having that negative sign, now the computer knows the direction should be in the negative x in order to get the maximum y value change. Now keeping this in mind, now let's go to the 3D figures. Now if you look at the figure, this is the x-axis. I have plotted f of x comma y equal to x square. You can see that the function is not dependent on the y. If you take a slice of this, you can see a two-dimension parabola like this. When you stack multiple parabolas one after other, one after other, one after other, that's when you get this kind of shape. For every value of y, there is a parabola. Now if I ask you what is the gradient distribution in this shape, just apply the thing whatever we have learned previously and then try to tell me what the gradient is at this particular point. Now you have two directions to move. One is in the y direction and one is in the x direction. If you move in the y direction, it's constant. If you fix the x, any given y, you basically have the same value of the function. So when you move in this direction, your height is not changing, it's constant. Now if you move in the positive x direction, then you can see the y value is getting increased. And similarly, if you are at this point, now if you move in the positive x direction, you can see the y value is getting decreased, and if you move in the negative x direction, then the y value is getting increased. That's how intuitively you can say at this point the gradient will be pointing in this direction for all negative values of x, and for the positive values of x, the gradient will be pointing in this direction. As it is not having any y component, the gradient will be only pointing in the x direction. And mathematically, if you see the gradient distribution, it's nothing but 2x comma 0. At x equal to 0.5 and y equal to 0.5, the gradient vector will be having fx is 1 and fy is 0. There is no fy component, so the resultant vector is only in the x direction. Now if I overplot this in this above field, then we'll get this interesting plot. If you see clearly, for all the positive x-axis, you can see the gradient is pointing in this direction, and for the negative x values, it's pointing in this direction. I'll just rotate it so you can have better view. So this is the bottom view and this is the top view. You can see all the positive x's are pointing in this and negative x's are pointing in this. Now let's try to see for the function f of x comma y equal to x cube. So we all know x cube looks in the 2D, it's something like this one. When you stack multiple x cubes for every y, then that's when you get this 3D structure. Now same, you take any given point. If you fix the x, then the y value is constant because the function is not dependent on the y. Now you try to move in the positive x direction. If the y value is changing, then well and good. So the gradient will be pointing in that direction. But when you are at negative x and if you try to move in the positive x direction and the y value is getting increased, in the previous case it was getting decreased. In this case, if you move in the positive x direction, the y value is getting increased. So the gradient is also pointing in the positive y direction. Similarly, at even these points and all these negative x values, the gradient is pointing towards only right direction. And mathematically, if you want to compute, then if you calculate the gradient, the fx component is 3x squared. Always the fx is positive for any value of x. So that's how you get it mathematically, but intuitively you can look at the figure and try to go in the positive x. If value is increasing, then yeah, the gradient points in that direction, and if value is decreasing, the gradient is pointing in the opposite direction. Now, keeping this in mind, let's test our understanding for this. I have f of x comma y equal to y square. Here you can see this axis is y. Previous one was x square and this is y square. For every x value, there is y square parabola, and now you stack multiple parabolas behind each other. First, intuitively, if you see at the figure, let us say at this point, if you fix the value of y and now you try to move in the direction of x, the value of the function is constant. The function is not changing the x direction. If you move in the positive y, then your y value is getting increased. That's when you realize the gradient should be pointing in this direction. Yeah, exactly correct. And coming to the negative y, if you move in the positive y, then you can see the y value is getting decreased. Hence, the gradient should be pointing in the opposite direction. Mathematically, when you compute it, you get 0, 2y. Here you can see the fx component is 0 and fy component is 2y. Gradient field is only due to the fy component, and you can see here there is no fx component. If you overplot these both things, then here you can see this is a y-axis and this is the x-axis, and it's similar to the previous one. For the positive y value, it's pointing in the positive y direction, and for the negative y, pointing in the negative y. So far we have understood, we got to know a little bit idea of the gradient. Now let's make the figures a little more complicated.